Hello, my name is Henshaw and welcome to my presentation on the variation in the measured in-situ U value of an external wall due to temperature sensor location. The UK domestic sector is responsible for 29% of total UK energy use. The government targets an 80% reduction in CO2 emissions by 2050 based on 1990 levels. A key issue in achieving this goal is the performance gap, in which the use of predetermined U values overestimates the performance of a building when compared to the as-built performance. This results in the energy consumption and therefore the CO2 emissions of the building being greater than designed. For this reason, there is a need for accurate in-situ measurement of the building fabric.
So, what is a U value? ISO 7345 defines a U value as the heat flow rate in steady state divided by area and by the temperature difference between the surroundings on both sides of a flat, uniform system. It can be thought of as an energy efficiency rating for a building element, with a lower U value being more energy efficient. As can be seen on the right, the U value is typically measured using a heat flux plate to obtain the heat flux, Q, and divided by the internal to external temperature difference, measured using temperature sensors.
Many factors can contribute to variations in U value measurement, including environmental conditions, construction detail, and, what this presentation will focus on, measurement technique. The testing took place at the University of Salford Henshaw, which is a pre-1920s end terrace constructed within an environmental chamber, thus allowing measurements to take place under controlled conditions. The external wall consists of 222.5mm solid brick with 13mm dense gypsum plaster internally, with an RD-SAP U value of 1.7 watts per meter squared per Kelvin. Internally, the equipment consisted of 7 PT100 temperature sensors spanning from the wall surface to a distance of 300mm at 50mm intervals, 1 heat flux plate, 1 anemometer, and 1 digital temperature sensor at the centre of the room. Externally, there is 1 anemometer, 1 PT100 temperature sensor at the wall surface, 1 Type T thermocouple 100mm from the wall, and 1 digital temperature sensor located 1 metre from the wall, similar to using a single weather station in the field. It should be noted all PT100s were calibrated to 0.1 degree accuracy in a UCAS accredited laboratory. The test schedule consisted of steady state and dynamic conditions both internally and externally. All phases consisted of a single 8-hour measurement period, however some phases had a longer duration to allow the house to achieve a state of equilibrium. It should be noted that the error bars only consider the error due to temperature sensors and do not include any uncertainty relating to the heat flux plate. This is due to a single heat flux plate being used for all measurements, with a measured heat flux being treated in a similar way to that of a constant. Along the x-axis, we begin with the U value calculated using the internal surface temperature, and then increases at 50mm increments from the wall surface to 300mm. The final point is the U value calculated using the air temperature at the centre of the room. At each point, the different colours represent which external temperature was used, with blue using the external surface, orange using the thermocouple 100mm from the wall, and the grey using the digital temperature sensor within the chamber.
Here, you can see the results obtained during the dynamic external conditions. It can be seen that all U values increased relative to those obtained under steady-state chamber conditions. As with the steady-state results, there is little change to the U value beyond the 50mm distance from the wall. One thing to note is the U value calculated using the external surface temperature, the blue bar, is consistently lower than the U value calculated using either the 100mm or environmental external temperature sensors. However, with the exception of phase 6, this difference is within the overlap of the error bars.
Here, we can see the chamber conditions throughout the testing. There was little change in air velocity throughout the test phases. There was a noticeable drop in the phase 2 steady state test, which is likely due to the HVAC system not needing to do as much work to maintain the higher temperatures. Internal air velocity is not shown as any air movement was outside the sensitivity of the anemometer, resulting in mostly 0 meter per second readings. There is no considerable change to the U value when the internal air temperature was measured at a distance greater than 50mm from the wall. Further, there is no change when the temperature was measured at the centre of the room. This held true for both steady state and dynamic internal conditions. meaning it is relevant to both quasi-steady state measurements in the field and in use measurement campaigns where the household undergoes regular heating patterns. It can be seen that the U values obtained under dynamic chamber conditions were greater than those obtained under steady state. Some secondary findings, which require further investigation through repeated testing, are as follows. The data could suggest variation in U value due to external temperature sensor location is dependent on the external conditions. The sensor located 100 mm from the wall consistently yielded a greater U value, typically by 4%. The U values calculated using the surface and environmental temperature sensors yielded a similar result under dynamic external conditions, with the exception of phase 6, whereby the external surface temperature yielded the lowest U value. This is likely due to minor changes in the air velocity, or that the wall had not achieved a state of dynamic equilibrium. So, to conclude, there was no change in the measured U value when the internal air temperature was measured between 50 and 300 mm from the wall surface. In fact, there was no change when using temperature sensor at the centre of the room. One benefit of such a finding is that a single air temperature sensor could be used for multiple heat flux plate measurements, assuming all were on the same horizontal plane and that other environmental factors would not affect the measurement. Further research should focus on the surface to 50 mm range to find a minimal suitable distance for temperature sensor location. Secondary findings suggest U value variations of typically 4% when utilising external temperature sensors at varying distances from the wall. This, when considered over the full external wall surface area, could result in a difference of 5 watts per Kelvin to the total heat loss of the dwelling. Again, it must be stressed that this was not the primary focus of the investigation, with the 3 sensors used being different types and not calibrated to the same accuracy as the internal sensors. Thank you for listening to my presentation.